Hello everyone and welcome for the first lecture for today. And our guest is Stefan Nozinic from Serbia, from the Novi Sad, and his lecture is going to be a formal specification of systems, why and how.
Thank you everybody. Hopefully you enjoyed yesterday's Rakia workshop, and I hope that you did not encounter system failure yesterday. So for today, we are going to talk a little bit about formal specifications and why we need them sometimes, and how to use formal specifications to discover some bugs before we start implementing any system, any kind of system. So when I say system, I mostly it's meant like software, but it can be also hardware system, or it can be any system where we have some kind of interaction between software and hardware. So here we are talking systems in general sense. So this is an agenda for today. So I will give you first some motivating examples. So this is one really simple example to tell you about TLA Plus and how to specify one simple system, which will be one simple software function. Then we are going to talk a little bit more about theoretic stuff, what is TLA Plus and what does it mean to actually specify some kind of system, and then what I really like about any lecture is to actually give some real-world examples, something which actually happened on day-to-day job. And then I will conclude by giving you some tips and giving you some additional motivation to spend a little bit more time tackling this subject, because I think it is really important for everybody to understand and to be able to specify systems. Okay, so what we actually know, this is one simple diagram showing workflow of any system development. So it's a little bit simplistic view, but it can tell us different stages. So we start from design, then we implement some system, and then we do some kind of verification where we verify if our system is correct. Usually in software, we develop some software architecture, then we implement it in some programming language, do some integration, configuration, and then we verify it usually with unit tests and integration tests and system tests. That's okay, but sometimes we need a little bit more than this. So when you unit test a certain software package, what you actually can guarantee is that you covered some really small space of possible inputs. So when we want to actually prove that our software is working, we need something more. And that's why I put here theorem proving for verification. So if you ever used Lean, for instance, so this is interactive theorem prover, there are software packages which can actually mathematically prove that your algorithm and your implementation is working as intended. But it's a little bit expensive, you know, so you need to write a mathematical proof that your algorithm is working, and it's rarely used in industry. It's actually used for really mission critical applications. It's not used for, you know, software as a service web applications where, you know, if system fails, then there is no high damage for, you know, people lives and so on. But what we actually want to do is to catch some bugs in design phase. So before we start implementing any kind of system, we want to catch bugs in architecture and design specifications. So we need a way somehow to formally, first of all, to formally specify our designs. Usually, right now, people are doing this by writing some kinds of documents. So it's usually some kind of architecture document where you write in human readable language like English. You write your specifications, and then somebody else or you takes that document and actually implements it in a certain language and maybe in hardware and so on. So first of all, we need some kind of formal way to write specifications for our systems. And then what can we do with that formal specification? Well, we can verify it. We can check if our specification makes sense. So what do I mean by makes sense? So there's no bulletproof tool which will replace people's minds. So we still need to invest some effort in thinking about certain systems. But once we specify something in formal language, then we can run model checker and actually check if statements we want to state about certain properties of the systems, if they're true or not, given our specifications. So let's see some simple example. Let's take this C program right here. This is a really simple program. So here we have 3 lines of code, and in the first line we get some value. We get some value from external resource. It can be mass storage, it can be time, it can be random number generator, and so on and so on. So we basically get some value out of external resource. Then we increment that value, then we set that value back to that external resource. So you can think of it as reading from disk and writing to the same place in the disk. This is really important that we are writing in the same place. So this is pretty simple program. There's a reason I have put comments here saying start, middle, and done. We will use it later on. So how can we specify formally this system? Well, we all know that computers are basically state machines. And here, if I want to specify my system, I can create a state machine of all possible states where my function can be in. So first we start with I equals 0, meaning that we take default value. I know that in C it will be value from memory, but let's say for the simplicity that the default value of this integer I is 0 in the beginning. And then we have, if you programmed in assembler, you probably know that there is something called program counter or PC here. So program counter says at which line of at which instruction of our program we are currently in. So here, that's the reason why I have put comments here for you to be easy to see where we are at. And here I have PC. So here my state is represented by 2 variables, program counter value and this I value I will use. And let's say that this get value will provide us with some kind of integer in range from 0 to 1000. So in the first state, our integer I is equal to 0 and program counter is start. And then what are possible next states? Well, possible next states can be I equal to 0, I equal to 1, and so on until we reach I equal to 1000, and PC in every next state is equal to middle. So this is basically drawing all possible states what we can get from this program. And then for every next state we have increment, and that means that PC is equal to done, and for the first state here where I equals to 0, it will end up equal to 1, and where I equals to 1, it will end up I equal to 2, and so on and so on. So this is pretty simple. We can all do this manually because we had really simple program. What about this one? So here we don't have one function, we don't have sequential program, we actually have two threads. You can notice that there are no locking mechanisms here. So what we are doing here is getting value from the storage and incrementing I, and then setting value back. And then in another thread, we're also getting value from the same place, incrementing I, and setting it back, so writing it back to storage, right? But here, it's not so easy to draw a state machine, because right now we have two program counters, right? We have a program counter for the first thread, and then we have program counter from the second thread. Then we also have two I variables. Why? Well, because this is local variable, so we also need to take that into account. And one important thing here is that order of execution is it can be in different order. So basically, I can execute first thread first, and then second thread, or I can execute first line of the first thread, and then first line of the second thread, and then second line of the first thread, and then second line of the second thread, and so on and so on. So not only that we have four different variables, we also have different behaviors, meaning that different orders of execution. And you can imagine that drawing state machine for this one wouldn't fit on a slide of this presentation. That's why I don't have it in the presentation. But even if you take one big piece of paper and try to draw it, you will have a really hard time actually drawing state machine for this program. Or this one. So this is even complicated one to draw state machine. You can see that this is pretty simple function here, but actually drawing state machine for this one is really complex task. Why? You can see that we are getting some messages from network and then checking these messages against some kind of type of message. And then based on that, we do something with that data. And then we are sending messages to nodes. And now, what are nodes? Well, these are nodes we are connected to. So this is some kind of distributed application we are working on. So here we, for instance, may encounter errors during network communication. This is one possibility. Then we can also encounter that sending some messages, can fail, or we send messages in different order, or when we send messages and when they are received on target nodes, they can actually be received in different order than order we send them. So that's basically it depends on which protocol we use. Are we using TCP, UDP, and so on? So actually designing that kind of thing in a sense that we want to draw state machine is really complex task. Now, why we want to draw state machine at all? Why we are interested in actually creating state machines for these complex systems? I mean, they are not complex systems, but to draw state machine for that is really complicated task. But why we want to do that? Well, what we actually want to achieve is to check if certain properties are true no matter what happens to our system. Imagine that you have consensus protocol. So in distributed systems, you have something called consensus, which basically means that nodes in one cluster need to agree on specific decision, on specific value. And you want to actually check if this distributed algorithm called consensus actually produces only one decision. So you want to check something called liveness and safety properties. So when we talk about distributed systems, safety means essentially that nothing bad happens, meaning that there's no something bad happening to our system. In our example of consensus, that basically means that system will never decide on two different values. So you cannot have one node deciding on one value and then another node deciding on another value, and then to have your system basically finish up with actually, some kind of conflict or something like that. Also, there is another type of property called liveness property, where you want to check that actually something good happens out of this algorithm. In our consensus implementation, that would basically mean we want actually to decide on some value. In the end, we want actually to find some decision. We don't want our algorithm to run indefinitely long, to keep deciding and fighting for certain values. We actually want to finish up with single value decided eventually. So these are kinds of things we want to check. When you implement some kind of systems, you want to check if these features are satisfied, if these properties are satisfied. And that's why you want to actually draw a state machine, because you want to check if in every possible state, whatever can happen to our system, we will actually end up having some properties where we can guarantee that they are satisfied. But drawing state machine is really complicated to do manually. So what we can use certain tools to do that for us. So this is pretty, labor-intensive task, and whenever you have something labor-intensive, you can actually leverage computing power to do that for you. But in order to do that, automatically we need some kind of formal way to specify our design. We need a formal way to specify. We need a formal way to specify what are the variables we are working on, what are the next possible states given the current state, what is the initial state. So we want to specify what are the valid states we want to have in our system, and what is the next state given some kind of valid state. And then we also want to specify properties we want to check against. And by the way, you can have multiple initial states. So in our example, we had only one initial state where PC was equal to PC was equal to start and I was equal to 0, but we can actually have multiple initial states. So what we need to actually tell in formal specification is that what are valid state for our state machine. If we can do that, then we can actually have state machines produced for us, and then for every possible state, computers can actually check our statements. So I will go back to our simple example where we are working with this program with 3 lines, and let's see how we can specify it in TLA+. So TLA+ is a language where you can specify these kinds of state machines. And there is something called TLC. TLC is model checker, meaning that when you have your formal specification for a certain system, then model checker can traverse all possible states in your state machine, and model checker can check for statements if they are true or not. So here you can see that I have two variables, as I already mentioned. So this is I and PC, and by the way, this can be written in a text file. So this is actually written in text file. What I did here for the purposes of this presentation is that for TLA Plus you can actually export it to LaTeX, and in LaTeX you can actually export it to PDF. So that's why you have these fancy symbols here. But it's actually written in text file. You can version control it in Git and in any possible version control system. And you can also keep these specifications next to your source files for your implementation. So we have two variables, PC and I, and then I want to tell what is the valid init state. So for me, valid init state is the only state where I is equal to 0 and PC is equal to start. So this is not assignment, so be careful about that. So this is not assignment, we are just specifying what is the valid init state. So imagine you have like infinite number of possible states, and we just want to tell our model checker, okay, this is valid initial state. This is the state where PC is equal to start and I is equal to 0, right? And then, given the current state, we want to tell our model checker what is the valid next state. How do I do that? Well, I have my PC and I, and I want to tell my modeler checker what is the next possible state by giving what is the valid next possible state. And I do that by comparing I prime and PC prime, meaning that so I have one tuple of I and PC, and then I want actually to tell, okay, what is, given the I and PC, what is the valid next next pair of values. And here you can see that I can be part of set from 0 to 1000, meaning that our get value can return some kind of integer between 0 and 1000, and only possible next state for PC is middle. So if my PC is equal to start, then next PC needs to be middle, and next I can be any number from the set from 0 to 1000. And if PC is equal to middle, then what are my next possible states? Well, for I, it will be previous I incremented by 1, and PC, only valid value for PC will be actually done, right? And every other state, so this is why I have here else part. So every other state is not correct, is not valid, and that's why I'm putting here false, meaning that whatever else happens in my space of possible states, it is not correct. And as last line, I have my statement. So this is something I want to check, and what I actually want to check is that always, so this is here, this square here, meaning always if PC is equal to done, that implies that I will be greater than 0, which we know that it will be true, because if we get 0 from our mass storage device, then we will increment it to 1, and for every other value we will also increment it by 1, so we will never get 0 for I when PC is equal to done. So this is basically it. So we specified our 3-line program. But you can imagine that given my previous examples, this can be really hard for humans to write, because we need to think about what are the possible values of PC. Do I have one program counter? Do I have 3 program counters? And so on and so on. So we need something actually more sophisticated and more, let's say, programmer friendly. And there is another language called PlusCal, where we can actually specify something much like usual programs, and there is a compiler which will translate that into TLA plus code, and then this TLA plus code we can actually model check with TLC. So I want to give you some, how much time I have? Okay. So I want to give you some real world examples. So this actually happened, and this is how I actually discovered certain, properties. So this is something which happened on day-to-day job. So we have a system of 3 nodes, meaning that they are connected to network and they can communicate to each other. And actually I have diagram here. Okay. So we have 3 nodes, and every node is running one instance of certain service. So that service has responsibility to serve some requests from clients. And when we have some requests from clients, we do some kind of load balancing, meaning that some requests from some clients will go to node 1 and process 1. So these processes are instances of our service. Some requests will go to node 2 and process 2, and some requests will go to node 3 and process 3. But since this is distributed system, we need to handle specific cases. What happens if one process is stuck? So one process can be stuck due to malfunction of certain things which are accessed by that process. And in our implementation, what we want is actually, we want to design something where if process is stuck, we can simply kill it and restart it back, and it will be running all over again. So that's fine. This is the easy part. The hard part is, what if node 1 is down? Meaning that node 1 got rebooted for some reason. We still need to continue operation, so we need to be reliable. We need to provide reliable service. So in order to do that, we need to load another node a little bit more. So what we will do, we will actually fail over process 1 to node 2. That way, node 2 will actually serve twice as much requests as before, because right now process 1 is running on node 2. And when node 1 is back up again, we will actually fail back that process 1 and continue normal operation. So this is kind of thing we need to support to in order to actually create a reliable system. So we want actually to load certain nodes a little bit more in order to serve everybody. Okay, so now I will show you how to specify this thing, and together we will check if our specification makes sense. So I will specify some properties, and then we will see if what model checker will give us. Okay, so let's see. Okay, hopefully you can see. Can you see text, or I need to zoom in a little bit? Okay. Is it better? Okay. So, in order to specify our system, what we will do, we will write PlusCal specification, and we will actually, so this is actually translated code into TLA plus. So this one we don't write, so you can see how complicated it is. But this one is actually simple. So here what I will do, I will have a set of alive nodes, then I will have mapping instance owner. So what is instance owner? This is node on which certain instance of service is running. So in normal operation, service 1 will run on node 1, service 2 will run on node 2, and so on and so on. But in our case, here we have that owner of process 1 and process 2 is the same, meaning that owner of process 1 and process 2 is node 2. So this is what node owner actually tells us. What is the node on which certain service is running. Then we have instance stack to indicate okay. So we have instance stack to indicate if certain service is stuck or not. So this is some kind of function which maps integer from 1 to 3 into Boolean value, and the initial value is false, meaning that everything is good. In the beginning, everything is good. And then we have a set of killed instances. So we are not modeling process of killing. So we will just say that killing the process means that we will just append it to set of killed processes, and when we restart the process, we will actually remove that element from the set of killed processes. So you can actually see that when we are specifying systems, we are not actually writing programs, which means that we can actually change level of granularity we want to have. So here I don't model actual killing. So we all know that killing process is not so simple. So it's not just adding certain elements to set and removing these elements from set. It's actually much complicated task. You need to invoke system call, then kernel needs to do something, then some states in process tables are changed, and so on and so on. But for the purpose of our specification, we don't care about actual process of killing certain instances of the processes. Okay, so we will have some service called heartbeat protocol. So heartbeat service will actually check if certain service is alive or not. So here we are not also modeling this kind of communication. So in practice, usually services need to respond to heartbeat ping for heartbeat requests, giving some kind of response. In that way, heartbeat service knows what are the processes which are alive and what are the processes which are stuck. But for our specification, we don't care about it either. We just say, okay, we just want to, check if service is alive. So we will model it as by checking this function, the value of this function. Instance is stuck, and this self here means that I'm checking if instance of my for my node is stuck or not. So here you can see that we are writing this program for three nodes. So TLA plus actually will try and run all possible execution orders which can happen. So for instance, we can have everything run by node 1, and then node 2 can be run later on, and so on and so on. So things don't happen in synchronization. So here we are saying that this algorithm will be run by 3 different nodes, and we will let modulo checker to check all possible behaviors. So every node will check if process is stuck, and if it is stuck, then it will restart the process, meaning that it will unstuck it by just restart it. So it will kill it, and then it will restart it again. And that way, what we are doing here, we are removing our process instance from the set of killed processes. But in order to check some properties, we also need to implement external events. So it's not enough to implement what our nodes are doing. We also implement what we want to happen outside of our system. And here we have additional behavior which actually can have. So what I'm doing here, I say, okay, while my set of alive instances is not empty, what I'm doing, I'm either rebooting the node or making some process stuck. So what can be possible behavior for this kind of thing? So for instance, node 1 can check if process is stuck. Then we can reboot node 1. Then node 1 can restart service. Then node 2 can be rebooted. Then node 3 can actually have instance marked as stuck, and so on. So this is one possible behavior what we can have. So this is basically it. And what I also want to specify is this statement here. So it looks like a little bit, complicated thing. If you programmed in LaTeX, you will probably, understand what are these things mean. So here, basically, I'm saying that for all nodes, what can happen eventually, if process is stuck at some point, then that will lead to either process being unstuck by somebody, or my node is only a live node, or my node is killed, meaning that my process is killed. So if I have process which is stuck, it will be either restarted, killed, or nothing of this if my node is only node available in system. Okay, so let's see, can we model check this? So can we check if this statement is true given our specification? Okay, so TLC model checker will run all possible states for our state machine, and actually it will throw error. And you can see that it found some kind of behavior which caused our statement not to be true. And it will also tell you the behavior which caused our statement not to be true. And this is what can happen to system causing our statement not to be true. So this is all the steps which can happen in order, which will actually end up in a state where our statement is not true. So if you take a look here, what we can notice here is that, let me go back to this one. So let's say that I have this situation, and let's say that process 2 is stuck on node 1. Process 1 is stuck on node 2. So this process here is being stuck. Okay. So then, if process 1 is stuck here, what will happen given our specification? We can go back to our code. You can see that we are actually checking if only, in this case, only process 2 is stuck or not. So on node 2, we will check only process 2, and then we will kill process 2 if it is stuck. But here we have a situation that process 1 is stuck on node 2, but we are not checking that if this is stuck or not. And that may cause that process 1 is stuck basically forever if node 1 is not rebooted. And we cannot permit that. So this is forbidden thing to do. So this doesn't satisfy our statement we have given. So there's a fix for that. I have already. Okay. So this is a better version of our specification, and essentially what we are doing here is when we are checking if something is stuck, we actually check all processes running on that node. So not just a respected process instance for that node, but actually everything running on that node we are checking if it is stuck or not. And then we are killing everything which is marked as stuck. So I just changed this part of the specification. This part of specification I did not change because this is something we shouldn't actually change. These are external events, and my properties stay the same. So my property states the same thing as in previous implementation. So let's see how this one performs. So again, TLC is running all possible states, and now it says success, meaning that, okay, my property is true for all possible states. And you can see actually how many states we have here. So there's no possible way that a human being would be able to draw state machine of this kind of thing. So this is really big number of possible states in which our system can be in. Imagine that we also went into higher level of granularity, meaning that we can also implement like the whole process of killing something, like sending it back to operating system. We can also specify network. We can also specify certain things which are not implemented here. So we can go into more granular specification, but also take into account that once you go into more granular specification, then number of possible states is higher, and it will take a little bit more, I mean not a little bit, but actually more time to calculate all possible states. But sometimes that's fine. So basically when we are specifying, we can actually choose, we can have a like trade-off between the speed of model checking and how many things you want actually to check. Okay. So, in conclusion, before I conclude, I want also to give one reference. So there is a YouTube channel. The creator of TLA Plus is Leslie Lamport, and so the same guy who created LaTeX, and the same guy who created a bunch of distributed algorithms. So basically, the guy for distributed algorithms. So he has a YouTube channel giving some course on TLA Plus. So you can also watch it. So you can just type TLA Plus course in YouTube, and actually you will see a bunch of lectures. It's really fun. I mean, he's changing hats all over the place, and changing clothes during the lecture. So it's really fun. So what I want to conclude with is that formal specifications can be used to detect bugs in design, and it is always better to detect some failures in design before you actually start implementation, because it's much cheaper to detect something in design before you detect it in implementation by some verification methods like unit tests, integration tests, or maybe theorem proving. But when you go to theorem proving, it's maybe too late in terms of saving financial assets and costs. What we can check actually is a lot of things. So we can check if our algorithms or our systems are terminating. We can check liveness and safety properties I talked about. We can also check correctness of certain algorithms. We can also check type correctness, meaning that if our data produced by our system is having correct type, meaning that if I want to have integers, do I always have integers, or sometimes I get something, you know, crazy or something which I don't expect. And also there are some research efforts to use TLA Plus for specifying smart home systems where the main goal is to check for some security violations. So it can be also used to check if there are some security bugs in our specification. For instance, if you are specifying some kind of protocol, you don't really want to actually have a protocol which has security vulnerabilities before you start implementing it, because when you start implementing it, then it's really hard to change architecture sometimes. So yeah, that's it. So if you have questions, this is our gossip session where you can tell, you know, everything what bothers you and so on. So yeah, thank you very much for your attention.
So thank you, Stefan, very much for the lecture. Does somebody from the public has a question?
Yep. You hear me? Yeah. Thank you for your talk. It's very interesting. It's not that we often hear about these things in the industry. So what would you say? What is like a threshold when formal methods are becoming economically feasible?
Meaning that when they become practical.
Yeah.
Yeah. Well, I would say if you have, for instance, systems making of, you know, multiple different software packages, or you have some kind of network communication where you want to have like distributed system and so on. If you have some kind of protocol, I think at that point the main goal of creator of the TLA Plus was actually to prove that certain distributed algorithms are working correctly. So that's definitely one application where I think it needs to be must. Also, whenever you specify some kind of network protocol, it can be also useful to specify it in TLA Plus or PlusCal and then translate it to TLA Plus. I wouldn't say it is much practical for simple software applications consisting of monolithic architectures where you don't communicate with anybody. I think it's maybe too much, you know, to use TLA Plus for that kind of thing. But if you have some kind of, you know, protocol or distributed application, then that it's definitely a viable thing to do.
Okay, thank you.
Is there somebody else?
Hi, sit on. Okay, I would just like to ask: is this something you use like on your day-to-day job for? And if you do, what's like the what's the part where you decide that this should be implemented or documented, and when is it not? Like, when does the value of specifying this become greater than the like not doing it?
So. Sometimes it's really hard to, you know, explain certain things to management. And you know, if you tell management, you know, we need to specify something formally and then model check it, they can tell you like, okay, but why do that? It's really, you know, financially, you know, expensive. Can we just go into, can we write a simple document in, you know, Google Docs or Word and then start implementation? So you need some kind of you know, convincing to do. So what I actually did is that we found a bug in certain things in our, you know, systems. And like I'm working in a company which develops distributed systems, and it develops, you know, on-premise cloud software. So what we actually did is that there were some bugs, and I actually specified these kinds of systems to in TLA Plus, and then run model checker, and then model checker actually discovered these bugs and a bunch of more bugs. So I would say that what you can actually start doing is taking something which already exists and trying to specify it, first of all, to better understand. So it's always, you know, better to formally specify something, because that will make you better understand some systems. So it's always easy, you know, to read document, but do you actually, you know if something is, you know, correctly written or not? And until you start specifying it, you will actually see a lot of things going wrong, or which doesn't make sense, and so on. That's one thing. So it can be also used to communicate things to yourself and to your teams. And you can also start like specifying simple systems, you know, in your day-to-day job, and actually trying to find behaviors and, you know, certain kinds of things which can actually fail your implementation. So I would start from that. I wouldn't start actually specifying something from scratch, but then as you know, gain more knowledge and practice, then you can actually start specifying systems from scratch. But you also need to take into account that you don't need to specify everything. So having, you know, some kind of threshold for granularity is okay. I mean, you don't need to specify up to TCP level stuff. So it's redundant sometimes.
Anyone else available? We still have a few minutes.
Yeah, we have 5 minutes, I think.
Okay, I guess that's it. Nobody's interested, and thank you. I'm sorry.
Thank
Thank you, Stefan,
Thank you.
for the great talk.